Hi, thanks for joining me. Today I'm going to be sharing a problem, and I wasn't actually too sure if I wanted to share the solution to this problem because it doesn't really follow an intuitive line of reasoning. However, it is logical, it does make sense, and it does solve the problem, and the problem itself is pretty beautiful. So I thought in the end I would share it with you guys. Anyway, this comes from the IMO American Team Selection Test from 2007, and this is problem 3. We want to find the value of theta given the following three pieces of information. Theta is between 0 and pi over 2, cosine of theta is irrational, and there exists a positive integer k such that cosine of k theta and cosine of k plus 1 theta is rational. So just from these three pieces of information, we should be able to determine the value of theta. Now this problem was sent to me by a viewer, and in fact I've stated the problem slightly differently. Originally the problem actually stated the value of theta and then asked you to prove that that was indeed true, but for this I've kind of left the value of theta, or I've not written down the value of theta, and we're just going to essentially derive it. Anyway, if you want to have a go at this pretty challenging problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so the first part of this solution is to state and prove a lemma. And this lemma says that there exists a monic polynomial Sn of x with integer coefficients with the property that Sn of 2 cosine of alpha is just equal to 2 cosine of n alpha. So let's quickly break this down. What does monic mean? Well, that just means a polynomial where the coefficient of the term, the biggest degree term, is 1. So for example, x cubed minus 4x plus 1 is monic because the coefficient of the term with biggest degree, x cubed in this case, the coefficient is 1. So that's what monic means. This Sn of x is just what we're denoting the polynomial, and this guy here just means polynomials with coefficients in the integers. And we have to have this property here. Sn of 2 times cosine of alpha is equal to 2 cosine n alpha, and this is for any real value alpha. Let's prove this. So the proof is just going to be by induction on n. So let's just define the base case one. So S1 of x, we're just going to have equal to x, and S2 of x is just going to be x squared minus 2. Both of these guys here are monic, because the coefficient of x is 1, coefficient of x squared is 1. And they all have integer coefficients, and we just need to check this property here. Well, for the case n equals 1, it's pretty obvious. When I plug 2 cos alpha in here, I'm going to get 2 cos alpha there, which is the same as 2 cos of 1 times alpha. When I plug in 2 cos alpha here, I get S2 of 2 cos alpha, which is equal to, when I plug this in here, is going to be 4 cos squared alpha minus 2. So if I factor out a 2, this is just equal to 2 lots of 2 cos squared alpha minus 1. But use our double angle formula, this here is just 2 cos alpha, 2 cosine of 2 alpha, like so. And that gives us that guy there. So that's the first two base cases done. And as I said, we're going to proceed by induction, kind of just using our double angle formula. So I'm going to claim that this guy here works, Sn plus 1 of x just being equal to x times Sn of x minus Sn minus 1 of x, like so. So firstly, it's clearly a polynomial because this is a polynomial, this is a polynomial, and I'm just multiplying up by x. It also has integer coefficients, because this does, and again, multiplying by x doesn't do anything, it doesn't change the fact that you've got integer coefficients, it definitely does do something, and also this is of degree n plus 1. Yeah, I should have said here in the statement that Sn of x is of degree n, and yeah, so S1 of x is degree 1, S2 of x is degree 2, this guy here is of degree n plus 1, because this is degree n times by x. Okay, and we just have to check this property here, and that kind of just follows from the double angle formula. So Sn plus 1 of 2 cos alpha is equal to 2 cos alpha from this x here, times Sn of 2 cos alpha, but by assumption, that's just going to be 2 cos n alpha. And similarly, Sn minus 1 of 2 cos alpha is just going to be minus 2 cos n minus 1, oopsie, of alpha, like so. And we just need to check that this thing here is equal to 2 cosine of n plus 1 alpha, but that just follows from the fact that if I look at cosine of n plus 1 alpha, and then add on cosine of n minus 1 of alpha, just using our double angle formula, this is going to be equal to 2 cos alpha cos n alpha. Okay, and then just rearranging this by subtracting cosine of n minus 1 alpha from both sides, and then multiplying both sides by 2, I get 2 cosine n plus 1 alpha is equal to 4 cos n alpha minus 2 cos n minus 1 alpha, which is exactly what I have here. So indeed, Sn plus 1 of 2 cos alpha is equal to cosine of n plus 1, or sorry, 2 cosine of n plus 1 alpha. And that completes the proof. So there exist these polynomials, these monic polynomials with integer coefficients, which have this property here. And as we'll see in just a second, that's going to be very, very useful. Okay, next thing we have is another lemma, and once we combine the result of this lemma and the previous lemma, we'll be able to solve the problem. This lemma says that if we have cosine of alpha being a rational number, and alpha equals r times pi for some rational number r, then cosine of alpha must be one of these values here, 0, plus or minus 1, or plus or minus a half. Okay, so let's prove this, and we're going to use the lemma we just proved. So the proof for this is, well, because alpha is equal to r times pi, and r is rational, the fact that r is rational means that there exists an integer n such that r times n is an even integer. It's an even integer. Okay, so if r is, say, p over q, then just let n equal 2q, and then you'll get that r times n is just 2 times p, so something even. So there exists n such that rn is an even integer. Then what we're going to do is consider Sn of 2 cos alpha, 2 cos alpha. Well, this thing here is equal to, by the lemma, 2 cosine of n alpha, but alpha is just r times pi, so I can replace this with r times pi, and now we've got nr, which is an even number, times pi. Cosine of an even multiple of pi is just 1, so this is just going to be equal to 2. So Sn of 2 cosine alpha is equal to 2. But if you remember what Sn was, it's a monic polynomial, and it has integer coefficients. So if I consider p of x, which is just going to be Sn of x minus 2, then this guy here is also a monic polynomial with integer coefficients. And notice that p of 2 cos alpha is going to be 0 because of this line here. So that means that 2 cosine of alpha is a root of p of x, and by the rational root theorem, because we know cosine of alpha is rational, so 2 cosine of alpha is also rational, it must be that 2 cosine alpha divides the constant term of this polynomial here. We don't know what that is, but we do know that it's going to be an integer. So 2 cosine alpha divides an integer, so that means that cosine of alpha, or 2 cosine of alpha, must be an integer. So that must mean that cosine of alpha is a half times an integer. But remember, cosine of alpha has to be between minus 1 and 1, so that tells us that cosine of alpha must take one of these values here. It can't take any other value. And that proves this lemma here. So now we've proved 2 lemmas, one to do with monic polynomials with integer coefficients, and another to do with if cosine is rational and alpha takes a particular form, then cosine of alpha is limited to a very few values. Anyway, let's use both of these lemmas to solve the problem. Okay, so the next line to this argument just involves a lot of ugly algebra, so I'm not going to bother through writing it all down. I've written it down already, and I'm just going to walk through it. So the first line I've written down is cosine of n plus 1x equals 2 cos x, 2 cos nx minus cosine of n minus 1x. Here, x is just kind of an arbitrary variable. Now this just follows from the double angle formulae. Now the reason I've written this down is because, well, if cosine of x is rational, well, by this argument here, we can use induction using this line here to say that then cosine of mx is rational for any positive integer m. So if cosine of x is rational, and, x here is a positive real sort of number, and if cosine of x is rational, well then notice that, well, cosine of 0 is 1, and that can be thought of as cosine of 0x, so that's certainly rational. So we have cosine of 0x and cosine of x are rational. So then just using this line here, we can get that cosine of 2x is rational. So if n was 1, we get cosine of 2x here is just, because this thing here is rational, this thing here is rational, this thing here is rational by assumption. And then continuing inductively, we can get that cosine of mx is rational for any positive integer m. So this line just tells us that if cosine of x is rational, then so is cosine of mx. Okay, the next two lines are written down just follow from the double angle formulae. Cosine of k plus 1 theta is cos k theta cos theta minus sine k theta sine theta, and cos of k squared theta is cos k squared minus 1 theta cos theta minus sine k squared minus 1 theta and sine theta. Again, these just follow both by the double angle formulae. Next, I've introduced some variables r1, r2, r3, and r4. r1 is cosine of k theta, which is rational by assumption. R2 is cosine of k plus 1 theta, which again is rational by assumption. R3 is going to be cosine of k squared minus 1 theta, and this is also rational because of this line here, the fact that if cosine of x is rational, then cosine of mx is also rational, because this thing here is equal to cosine of k minus 1 times k plus 1 theta. And we know if we kind of let this guy here equal x and k minus 1 equal m, then we get that this is kind of cosine of mx. And so this thing here is going to be rational. And for a similar reason, r4, which is cosine of k squared theta, that's also rational because that's k times k theta. Okay, and we're also going to let x equal cosine of theta. So then just looking at these lines here, this one here and this one here, line 1 will give us this equation here, and line 2 will give us this equation here. So r2, which is just cosine of k plus 1 theta, is equal to r1x plus or minus the square root of 1 minus r1 squared times 1 minus x squared, and that just comes from the fact that sine squared plus cos squared is 1, and this plus or minus is just to disambiguate any square rooting, and this 2 here is pretty much the exact same thing but from this line here. And we get two equations involving r1, r2, r3, r4 and x, and if we rearrange them and then square both sides of each equation and then do some subtracting, it's going to simplify down to this nice equation here. 2 times r1, r2 minus r3, r4, x is equal to r1 squared plus r2 squared minus r3 squared plus r4 squared. Oh, that is a long bit of tedious and boring and uninteresting calculation and computation, but you arrive at this line here. And why is this interesting? Well, remember r1, r2, r3 and r4 are rational numbers, but x, which is cosine of theta, by assumption is an irrational number. So this thing here is rational, this thing here is rational, this thing here is irrational, so not in the rationals. Rational, 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 rational. So we've got rational equals rational times irrational, and that should be having some alarm bells. How on earth can we have an irrational times irrational equals irrational? Well, the only way that's possible is if the rational here, the thing that we're multiplying the irrational by, is 0. So therefore we must have that r1, r2 minus r3, r4 is equal to 0. And that's what all this boring and ugly computation was leading towards. r1, r2 minus r3, r4 equals 0. Now let's use this to solve the problem. Okay, so we just proved that r1 times r2 minus r3 times r4 is 0. So that's just cosine of k theta times cosine of k plus 1 theta minus cosine of k squared minus 1 theta cosine of k squared theta equals 0. I've written out the double angle formula or one of the double angle formulae. Cosine of a plus b plus cosine of a minus b is equal to 2 cosine of a cosine of b. And the reason I've written this down is because using this gives us this line here. Cosine of 2k plus 1 theta minus cosine of 2k squared minus 1 theta equals 0. So going from this line to this line, essentially for example this thing here, I've used a equals k theta and b equals k plus 1 theta, and then that's given me cosine of 2k plus 1 theta, that's given me cosine of theta, and that's going to give me 2 cosine of k theta cosine of k plus 1 theta, which is what I have up here, and this cosine of 2k plus 1 theta is here, and then I'll get a minus cosine theta, but when I do something similar with this guy here, I'm going to get a minus cosine of theta here. Anyway, you can check for yourself, using this line and this line, we can get to this line here, and then again, just using some double angle formulae, from this line we can get to this line here. 2 times sine of k minus k squared plus 1 theta times sine of k squared plus k theta equals 0. So again, we weren't done with the algebra, but now we've gone through most of the ugly algebra and just using double angle formulae. So when you think about it, there's not much too difficult about it, but it is just a bit long and a bit tedious. Anyway, we get to this line here. 2 times something equals 0. That means one of the somethings must be 0. So either sine of k minus k squared plus 1 of theta equals 0, or sine of k squared plus k theta equals 0. Either way, we're going to have that this guy here or this guy here is a multiple of pi, but then that means because k is an integer, this thing here is an integer, this thing here is an integer, either way we're going to have that theta is a rational multiple of pi. So theta equals r times pi for some rational number r. Now remember, we have that cosine of k theta and cosine of k plus 1 theta are both rational. And then we can apply the fact, well, because theta is a rational multiple of pi, then so is k theta and k plus 1 theta. But then we can apply lemma 2 to k theta and k plus 1 theta. So you have cosine of k theta is rational, and k theta equals r, let's say r1 times pi for some rational number r1, and cosine of k plus 1 theta is equal to r, is rational, and k plus 1 theta is equal to r2 times pi for some rational number r2. And then we can use the result of lemma 2, which then says that cosine of k theta and cosine of k plus 1 theta must take certain values, either 0, plus or minus half, or plus or minus 1. But either way, all kind of three of those, if you think about what values will give us cosine of, so what values of alpha will give us cosine alpha equals 0, what values of alpha will give us cosine alpha equals a half, or plus minus half, and similarly plus or minus 1, we get that all of them are going to be integer multiples of pi over 6. So cosine of k theta is an integer multiple, k theta is an integer multiple of pi over 6, and k plus 1 theta is an integer multiple of pi over 6. So when I look at the difference between the two, which is going to be just theta, because k plus 1 theta minus theta, that's going to be an integer multiple of pi over 6. So theta is equal to n pi over 6 for some integer n. But remember, we're assuming that theta is strictly between 0 and pi over 2, so that means that n is either equal to 1 or n is equal to 2. Because if n is 3, then we get 3 pi over 6, which is pi over 2, and that's not in the range because we're excluding the kind of boundaries. So n is 1 or n is 2, and the way we differentiate between the two is notice that if n was 2, this thing here is 2 pi over 6, which is pi over 3, which is 60 degrees, and cosine of 60 degrees is a half, which is rational. But we're told that cosine of theta is irrational. So that must mean that n equals 1, or in other words, theta is equal to pi over 6, and we are done with this long, exhausting problem. Theta can uniquely be determined just from those three pieces of information we were given at the start, which I think is pretty fascinating. Theta equals pi over 6, that solves the problem. As I said at the start, the solution is not very pretty, involves a lot of algebra, and I was a bit reluctant to share this video. However, the fact that we can uniquely determine theta from just three pieces of information, one, theta is in between 0 and pi over 2, that in itself doesn't seem that interesting, and then this kind of rational condition about cosine theta being irrational, but there existing this k and k plus 1 such that cosine of k theta and cosine of k plus 1 theta is rational. Anyway, to me the problem itself seems quite beautiful that we can solve it, but the solution less so. Let me know what you think in the comments down below. Anyway, I'm going to stop waffling. Thank you for sticking around for this whole video. I'll catch you in the next one. Have a great day.